It's getting there. It should get there anyway. So, they let you?
Clay's like the second string presenter. He only goes after I go.
Not quite sure.
Remember when he like subbed me out to do the job he couldn't, Jared? Remember how I was above everyone else so high that he had to bring a lower plebeian like yourself?
Okay, why is that?
Jared, you sound so
There we go. All right. Now, those of you, if you've got your calculators and want to follow along, that would be just fine. This idea of parametric equations. Now, this is one of those topics. I didn't take you. This is one of those topics. This is one of those topics that is in Calc 2. And we do some topics in Calc 2 as we go into here, and we will do some topics that are not on the AP test. So you'll see as we're reviewing for the midterm, this will not be on here. As we're reviewing for the final late in the year, there are several things you'll notice are not in there that we have done, which is fine. We're going to do them anyway because I think they're important and I know they're things you'll need, especially if you're going to be taking Calc 2. And they're good topics and they tie in with other things we're doing. Okay, so this is just an introduction to the idea of parametric equations. So they will show up. There will be at least one quiz in Chapter 4 where parametric equations will show up. So some of these additional topics we do, we're going to quiz over them and they'll be a part of our class. They just wouldn't be on the AP test. Okay, but there's certainly things you would see in a calculus class in college. So parametric equations. Now, what parametric equations are the ability to write an equation for both the x and the y coordinate. Now, normally what you do is you write one equation for the x and y coordinate, like y equals mx plus b, and that's what you did here. So what you had, and I don't want to spend a great deal of time on this, but what you had here, and you guys help me out with your linear equations, this 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, the Ranger started way out here, right? And the Lion, 50, he started, what, 51 miles north? So right there. Now, the Lion went 1/10 of a mile north and 0.3 miles east, so he took off kind of in this direction, right? And kind of had a slope of 0.3 this way and 0.1 that way, right? So rise over run, that would be what, 1/3? 1/3. Okay, so the Lion's path would be y equals 1/3 x plus 51. Just very simply, y equals mx plus b, the slope and the y-intercept. Okay, the Ranger, he walks 0.5 west and 0.6 north. So he's going back this direction. So he's heading in this direction like so. And he's going 0.5 back this way and 0.6 this way every minute. So that would be what, 6/5 would be the slope? And it's negative, isn't it? Because that line, we always talk about left to right, right, with our slope. So that's a negative 6/5 x. And then finding the y-intercept might be trickier. Probably what we ought to do is just pick our point, 100 plus 0. Probably be easier to just do our point slope form there, right? And so we could do that. Now, you guys have probably worked that out, I guess. What is it? Negative 6/5 x plus 120. Is that what it ends up being? Okay. So that ends up being the Ranger, the equation. Now, so what that does for us, those two equations, those are equations we're used to seeing. They have an x and a y in them. And what that will do is that will give us the location on the path of each one of those. So when x is 10. Now, but what's interesting about that is what we've been used to doing in calculus so far is a lot of distance and velocity and acceleration kind of things, right? And here's where this worksheet could have got a little confusing. And we talk about slope and velocity, were a lot of times the same thing, right? Rate of change, slope is rate, velocity is rate, and those things. And so I'm guessing there was could have been, usually there is, some confusion as you got a little later down into the worksheet. So we really want to talk about this. We've been used to equations where time was our input, right? And then distance was our output. That's not the case here. If I put an x in here, so like I put a 100 in here for the x, what does that x stand for in this problem? What is x in this problem? The distance east. And what is y? The distance north. So if we were to label our axis here, this is miles east, and this is miles north, and that's very different than many graphs that we've worked with so far this year. We've had minutes or hours or seconds down there on the x, and we've had distance up there on top, okay? And I say that because, now, I'm going to skip over the rest of this. Where do they cross? Well, you could just take this, set it equal to this. You could have graphed them on your calculator and chosen under somewhere in there in the calculator you could show an intersection. I'm not interested in that. You could solve that equation, just put those two equal to each other. It's just algebra 1, right? You just set those two equal to each other. It comes out to be x equals 45, and the y is 66, I believe, right? So that's where they cross at the point 45, 66, right? So we should all be able to do that. Now, how far is it from where the Ranger starts? Well, that would be the distance from here, this point, to there. Now, how do you do that? That's the distance formula. Now, the distance formula is nothing more than the Pythagorean theorem. Okay, if I want to know the distance from here to here, if this was 100, 0, and this was 45, 66, okay, then all I need is this distance, which would be the x-coordinate here minus the x-coordinate here. That's 100 minus 45, okay? And that would be this distance right here. And then I would square that. And then plus this distance here, which would be the y-coordinate, 66, minus the y-coordinate there, so 66 minus 0, squared. And then that'd be the hypotenuse if I square root that, right? It's Pythagorean theorem. It's just this squared plus this squared and then the square root. So when everybody says, well, I don't remember the distance for it, don't worry about it. It's Pythagorean theorem is all it is, right? It's this: subtract the x's, square it, subtract the y's, square it, then the square root of all that. That's your distance formula. So how far did they go? Now you'll see in a minute why you need that. So you come down to here, and it talks about at what rate are they traveling every minute. Now, you might have been tempted to say that the lion's rate would be his slope, which was 1/3, but that's not his rate, right? Because what are the units on the slope of that graph? The y over the x, right? That'd be miles north over miles east. What that means is the lion, it is a rate. Slope is a rate. Every single time, slope is a rate. It's just not the rate we want. We want miles per minute. That is not miles per minute. That's 1 mile north for every 3 miles east. Or it's 1/3 of a mile per mile north per mile east. Does that make sense? That's what that rate is. It's not the rate we want. We want miles per minute. So that's why we found in that earlier part how far he had traveled. So how far had the lion traveled? From 0:51 to 45:66. What was your distance formula for that? For the lion? 47.4 something, right? And then you needed to know how many minutes it took him to get there, right? Well, distance equals rate times time. If we want to know what this rate is, we need to take the distance divided by the time. Or maybe not, because I don't know that we know the time here, do we? We don't know how long it took for him to get to where they meet, do we? What do we know? We know the lion every minute. That's where this comes in. He went, what was it, 0.3 and 0.1? Don't we need to know that hypotenuse right there? Don't we need to know the Pythagorean theorem on that? And it's been a while since you guys did this, so you probably forget what you did. This is the secret on this. That's why they gave it to us that way. It goes 0.3 this way and 0.1 this way every minute. So if we do the hypotenuse here, 0.3 squared plus 0.1 squared, and then the square root of that, that will give us how far, because they're traveling on the diagonal, that will give us how far per minute, right? So you do that, and what was it for the line? I know some of you have it. It's like point something. 316 something something. So you've got to take distance divided by rate. So you're going to take 47.4 to whatever that number is divided by 0.316, and what was that? I'm sorry, 0.1316 is the rate. How long does it take would be the 47.4 something divided by the 0.316, and that came out to be what? Exactly? Did anybody get it exactly? Did it come out just... Here's the thing. If you round these, then that's going to make this maybe not exactly right. I thought this came out exactly at 150.
Yeah.
I think it should. Is this number right? But it's probably rounded, right? I mean, it's rounded. So what you need to do in a situation like this, you should leave these decimals as many, go out 4 or 5 decimals. I think it was exact. I haven't done this for a while.
Put those numbers in, it's exact.
Even those numbers right there? Okay. I think it's exactly 150. And what's the other one? For the, that was the Lion, right? And the Ranger?
110.
Yes. Okay. And that would be miles per minute. No. That was minutes. That was minutes.
Yeah.
That was minutes. Okay, what were the rates up here? This was 47.4 miles per minute, and then the Ranger was... Oh, yeah, I'm sorry. This is what happens when I try to get through this in a hurry. It ends up taking longer. 0.316 miles per minute, and the Ranger was 0.7 something miles per minute. So he's walking faster, right? Because he's going 0.5 and 0.6 every minute, and the Lion only going 0.1 and 0.3. Okay, the real question in all this, though, is what? Do they collide? Does the Ranger get eaten by the Lion, right? Now, if you just go by their graphs, do they collide? But what is that? Their paths collide. And here's where parametric equations come in. Because what we don't know, it took us a long time to get all the information. What we don't know is at any given time, where's the Lion and where's the Ranger? At any given time, where's the Lion and where's the Ranger? And that's where parametric equations come in. So we're going to finish the bottom half of this worksheet. So the real secret, now there's no calculus there, right? Matter of fact, calculus just kind of confused us there because we thought slope might be rate, and that might have just confused it, to be honest with you. But let's talk about this. So what we want to know is where was the Ranger, where was the Lion every minute? Well, the Ranger started out at 100, 0, and then he went backwards on the X to 99.5, and then he went up 0.6, and then another minute goes by, he's back that direction, and he's up another 0.6, and so you start getting a pattern here, right? You notice that the X column, every time T increases, it goes back, subtracts 0.5. So this would be 100 minus what, 2.5? So that'd be 97.5, and this would be 95, and all of a sudden you say, hey, there'd be an equation for that. It's 100 minus 0.5 times whatever T is. The Ranger's X coordinate is 100 minus 0.5 for every minute he's walking. And the same thing is true here. He goes up 0.6 every minute. So 5 minutes he would be up 3. And in 10 minutes he'd be up 6. And we realize it's his starting point plus 0.6 every minute. And we can do the same thing with the Lion. The Lion's X coordinate started at 0 and it goes up 0.3 because he's right. He goes 0.3 this way and 0.1 up. So his X coordinate is going to gain by 0.3 every minute. And his Y coordinate, which starts at 51, is going to go up by 0.1 minute or 0.1 miles every minute. Right? So here's what we have just found. We have found an equation, X of T. Remember when we've done that with Bismarck going east to west? X was actually our output because that was the distance and T was the time. So what we've done here is we've got two-dimensional motion. All of our motion so far has been one-dimensional. Vertical, we've got the balloon going up and down. We've got the car going along east to west to Bismarck. But now we've got two-dimensional motion. They're going both north and east, or north and west, and north and east, right? So the X for the Ranger would be this, and the Y for the Ranger would be that. And parametric equations come in pairs. That's not why they call them that. But the T is called the parameter. That's where the word parametric equation comes from. And that is a parametric equation. It's a separate equation for both the X and the Y coordinate. So it's another way of writing an equation of the regular equations that we've been used to working with. Now, what they're really good at is modeling motion. Now, the discrete math class here later on is going to do some work with projectiles. And I think physics class, Mr. Mandernack did that, right? You guys talked probably about vectors or whatever. I mean, that was basically parametric equations as well. Did you ever use the term parametric equations in physics? Okay. But that's essentially the same thing, the horizontal component and the vertical component, right? So it's very similar situation, okay? Now, we can do derivatives on this, which we're not going to get into right now, but the derivatives here would be then the horizontal velocity, the vertical velocity, right? And we can separate that out. Now, last thing I'm going to say about parametrics here, and then later we'll talk about the backside of this, but basically the backside is just about now graphing those on your calculator in parametric mode, not in function mode, but in parametric mode, and showing that you basically get the same graph and you get all the same answers to the questions you got on the front side. That's really all that's about. Okay, and then the bottom is just one separate thing with distance, which we'll do at a later time. The last thing I want to say about parametric equations is this. You guys last year worked with a parametric equation and didn't even know it. Now, you didn't write those as functions like that, but what is that equation right there? What picture would that make right there? That's a unit circle. X equals cosine and the Y equals sine. And T, when you learned last year, was theta. Theta was the parameter. It wasn't really time, it was radians, but it's the unit circle. It's the unit circle. And if you think about the equation for the unit circle, remember our equation for circles?
Yep.
X minus the center squared plus Y minus the center squared equals the radius squared, which is 1. That'd be x squared plus y squared equals 1. Wouldn't that be the equation of the unit circle? Now let's do a substitution. Let's substitute x and put cosine in its place. And let's put sine in place of the y. Right? Isn't that a true statement? Cosine squared plus sine squared is 1. Right? And that is exactly right. And remember all the work you did last year with ellipses? Right? What if I put a 3 in front of that right there? Now pretend the 3 wasn't there. Cosine has a range of values, outputs from what to what? -1 to 1. So that tells you, that top line tells you the x will go from -1 to 1. And the bottom line, sine goes from -1 to 1. So the y will go from -1 to 1, right? Oh yeah. Circle. Right? What if you put a 3 on the cosine? Now the x is going to go from -3 to 3, but the y is going to go from -1 to 1, and that's going to make an ellipse. That's just going to take that thing and stretch it. It's a really cool way to write ellipses, much easier than the way you wrote them last year. Remember the a's and b's and the foci and all that stuff, which is still good stuff to be able to find that, but it's a neat kind of connection to something you've already seen. Unit circle is really a parametric equation. Okay, so that's a good time to kind of talk about that because we're done with chapter 2. We're getting ready for chapter 3. And so we'll come back to that page another time, and we'll look at that some more. Okay? So that's what parametric equations are all about. All right, let's get started in chapter 3. So go ahead and get your notes out and play. This is where you're gonna start. Now, as we're getting ready to do that, I guess I should mention the cell phone thing. I don't envision this being a major difference for us in here. I'll be honest, I haven't even noticed. But I think what I like about this policy, I was even thinking about this weekend. I had a couple of friends of mine, and we went out to breakfast one morning just to sit and visit and whatever. And we always kind of laugh at ourselves because here we get together, go out of our way to get together to sit and visit, and we spend half the time, all three of us, on our phones. Like we were a bunch of teenagers, right? I mean, not only that, but there was a table next to us that we kind of laughed about. That there was a group of retired gentlemen that had to be 70 plus, and all three of them had phones. And there's an old joke about the old retired guys that get around and just talk about the weather, right? Which is what we do when we get old for some reason. And what's funny is all three of them were using their phones to talk about the weather. They all had radars pulled up, and they were talking about the snow that was coming. So they were comparing what weather out there. It was so funny. But anyway, whatever. It was just classic. So some things never change. But you know, maybe I use this example with you guys. I was telling my Algebra 1B class this, but it's not really a punitive thing. It's not supposed to be that. Because we've been there with that rule. I mean, the rule really has been in the past, and teachers have done this, that if your phone is out and it's not supposed to be, that they take it and they take it to the office and your parents have to come and get it. That's fairly punitive, right? I think the idea now is that the teacher may take it and you just have to get it at the end of class when you leave. So it's not meant to be punitive. It's more like, and I use the example of, you know, why does somebody like my age hire a personal trainer? You know, I know what foods are good and bad. I know what I need to do to lose weight. I know how to exercise. I mean, it's not rocket science, but sometimes you just have to be forced to do the right thing or to break habits, right? And maybe look at it that way a little bit. Maybe, and I know I'm the same way. I go out to eat somewhere, I set my phone out right on the table right by me, as I know most people do. And then when a text comes or something comes, I'm distracted by it. I'm using it. So by having to put your phones away, so what I'm asking you, and I'm not saying I'm going to be really good about enforcing this, but what I'm asking you is to just follow along with me. What I don't want to have happen is a principal come to me and say, you know, some of your students are telling other teachers, well, Mr. Clark doesn't make us put them away. You know, and then it's going to look bad for me. And then I am going to have to get tougher, right? So I'm just asking you, just put them in your bag. Right? Just put them in your bag. Just have them out of the way. But the one I am going to be kind of picky about, and I think this one is important because they have had issues with people with phones in the bathrooms and those kind of things, is that if you're going to ask to leave go to the restroom, that you show me your phone or leave it on my desk here. I might put it in that thing, or whatever. Leave it here or just show me, hey, here's my phone, put it back in your bag. So I am going to be kind of picky about that. Okay, so I may not ask. If you go to the phone, you know the rule, or if you go to the restroom, I may not ask, I may forget about that, so please help me out with that, and let's do that, because I think they are going to be try to be picky about phones in the hallways and stuff during class time, and then they're going to ask, where'd you come from? Whose class were you in? You know, so I've told you, that's the rule. All right, so anyway, so let's start talking about Chapter 3. What is Chapter 3 all about? Chapter 3 is simply about the rules of derivatives. You look at that assignment sheet I gave you, it's pretty short, okay? And it's short for a reason, because we've just got done the end of Chapter 1 and most of Chapter 2 talking about how we can use derivatives to find some important stuff. Now, we've been talking about graphs mostly, but local max, local min, global max, global min, inflection points, concavity, the chart, the number lines, the list of candidates, all that stuff. Okay, that's all really important stuff that we can do with derivatives. What we need to do is talk about how to find derivatives. We've just scratched the surface with that. How do we find derivatives? We've got a list of rules so far. We're going to add to that here in Chapter 3, and we're going to finish that list of rules. We're going to get to where, within the next 3 or 4 days, quite honestly, where we can take the derivative of any function or combination of functions that we can think of. Okay? And by next Tuesday, we are going to take our derivative test over Chapter 3. So it's going to be a really quick chapter. Now, this derivative test is a little different. Now, I'll talk more about it another day. But this test you have to take repeatedly until you get 8 out of 10 questions right. So it's just going to be 10 functions, y equals whatever, and you have to find y prime. There won't be any y double prime. You just have to find the derivative. And you have to get 8 out of 10 right. They're either right or they're wrong. So you got a sign wrong, you got any little piece wrong, it's wrong. You got to get 8 out of 10. Now your grade then on the quiz is based on how many attempts it takes you to get 8 out of 10. This is called a gateway test, right? I guess like a gate, like you can't get through it until you pass it. The first one will be on Tuesday in class. Any you have to take beyond that have to be outside of class on your own time, like at lunch or a free period or before school or after school, whatever. Okay? So obviously you wanted to pass the first time. Traditionally, the passing rate is somewhere between, I don't think I've ever had half the people get 8 out of 10. 25% is probably on the low end. Probably somewhere in the 30% range. I mean, 30 to 30, so a third, if you say a third. So we have roughly 50 people in class, so you might expect 15 to 17 maybe to get it the first go. Algebra is going to be a big piece of it too. Okay?
Yes. So if you get, say get 8 out of 10 on the first go, is that an 80 or a 100?
No. So 8 out of 10, 9 out of 10, and 10 out of 10 are the same thing.
Okay.
Right? 8, 9, or 10 out of 10, those mean you passed. So the first time, you get 30 out of 30. So you get 8 out of 10, 9 out of 10, or 10 out of 10. On the first attempt, you get 30 out of 30 in the grade. Okay? If you pass it, now, the next time, there's a time element and a number of attempts. So you get 2 more attempts after that to get 27 out of 30, which is still an A. So you really get 3 attempts to get an A on this quiz. Okay, so you think about maybe what your average quiz grade is right now. 3 attempts to get an A. Not bad, right? It should be a chance to really have a decent grade in the grade book. Should be. Okay, now, you have to take one of those 2 attempts. Now, we're going to run into Christmas break, so you certainly don't want to make it go over Christmas break anyway. So you really get that rest of that week, probably about a 3-day period to try a couple more times.
Have you ever had somebody go, past Christmas break?
Yes, typically people that go past Christmas break would mean they've tried 6 or 7 times. Usually almost everybody passes it by then. The people that go past Christmas break are the people who have maybe decided to give up, and maybe only do a couple. Yeah, I think I've got 7 of them made up, but I'm not sure I've had to even give the 7th. Yeah, I'm sure I've given the 7th or 8th one maybe. They maybe get just a little easier when you get that far into it. But at some point then, I do, and usually what I did kind of change is I did allow, at some point as we get towards Christmas, after you've maybe tried 3 attempts at least, that's kind of the minimum, and if you've tried 3, you still, because it goes 27 out of 30, and so you get 2 attempts, pass either one of those in the next 3 or 4 days, you can get 27 out of 30. Then if you go to the 4th and 5th attempts, it drops to 24 out of 30, which is still a B. Okay? And then after that, the next couple would drop to 21 out of 30. And at that point, I've said I would let people just kind of take your highest grade. Like, you keep getting 7, which would really suck. But if you keep getting 7, then I could, if you're already at the point where it's going to be a 21 out of 30 anyway, well, I'll just let you take the 7, let you take the 21 out of 30, and just call it good, right? Because that's the highest you can get anyway. And what I've done with some people is some people just gave up and never came in, and they got a 1 out of 10, and they never have tried it again, then they get a 3 out of 30 in the grade book, because that would be a 10%. Okay? So I've done that with a few people, right? But I'm probably going to make it a minimum of 3. So you can't really give up until after 3. If you get a 1 out of 10 and then never come in again, it'll probably go into the 0. Or if you get a 6 out of 10 and never come in again, it'll go into the 0. Okay, so you have to at least make that effort. Okay? All right, let's get into this now a little bit. So, one of the things that we've already done is we've talked about a bunch of these derivative rules. Now, don't write any of these down yet because you should have them all written down. If you got a sum or a difference, you just do the derivative, right? So we've got that. If you have a number on the outside, no, some of these are new down here, don't worry about those right now. So you got a number on the outside, it just hangs out there. Now there's a new one, those are the ones we're doing today. That's a new one. Now we get into ones we've already done. Now you notice I put a U there. We're going to talk about that U, why that's there tomorrow. Don't worry about it right now. It's just the power rule. Derivative of e is e to the u. Again, don't worry about this over here, but these rules we've already had. Logs, the exponentials, the other log rule, right, of another base, okay, sine, cosine, tangent, cotangent, secant, cosecant. So you see in our list of rules, we've got most of them. What we don't have at this point is what do we do when there's a combination of functions? If you're just adding functions together, that's not a problem. You just do them individually. You're subtracting. But the one we really have to worry about, and this is where, Clay, you're going to go to work now, is what if I want to do the derivative of x squared times sine x? Now remember, that's our notation for derivative right there. The other way I could write that is if this was on the gateway test and I gave you y equals x squared times sine x, and I wanted you to write y prime, right? That's kind of how the gateway test would look. But this up there, that says do the derivative of x squared times sine x. So, Clay, we're just going to not even try to figure out how to do it. We're going to let Clay do it. So, go to your calculator screen. Clay, yeah, just go to your calculator screen here. Okay, and we're going to go to the template next to the 9 there. We're going to grab our derivative rule. Okay, now this is going to be the next 7 days are going to be no calculator. We won't hardly ever use our calculator except for a few demonstrations because this test obviously is no calculator, right? Because the calculator just do derivatives for you. But it will be kind of your electronic solutions manual as you're doing practice for these. I've got a couple websites you can go to practice. There's a bunch of them in the book you can go to practice. And so sometimes the back of the book, we've talked about this, doesn't always write them in the form that you may have written them and you were curious if yours is correct. We talk a lot about how much you need to simplify, stuff like that. You know, you can use your calculator to see if you're doing them correctly. Okay, so let's put x squared times, I always put a times sign just in case because the calculator's funny that way, sine x. Because if this was x times sine x, you could not just write x and then sine. It would put those together as one word, and it would not understand that that was times. Now with an x squared it would, but I always put a times sign in there to be safe. Okay, hit enter. Now let's look at that answer. And let's see if we can figure out what happened there. Matt, what do you think?
Okay, so it did like the derivative of one of the variables, and then it added the derivative of the other one of the variables by itself. Like it took the derivative of sine x, which is cosine, and just combined that with x squared.
Yeah, you said added, but it actually multiplied them, right? I mean, I know what you meant by added, like put them together.
And then you add the derivative of x squared, and then leave the sine x.
So it's kind of like they took turns.
Yeah.
That'd be a good way to say it. You got two things multiplied together. What it did is it didn't just do the derivative of x squared, which is 2x, and the derivative of sine, which is cosine, right? Which would make kind of sense if it did, but it turns out it doesn't work. So we can't do that, okay? And we actually showed that with some power rule ones earlier that it doesn't work. This is called the product rule. For obvious reasons. Right? When you're multiplying two functions together, you take turns. Now, I would normally rewrite that the other way. I think the calculator likes to write the higher power. But I would typically think of this as do the derivative of the first one, which would be 2x, leave the sine alone, plus, then leave the x squared alone, and then do the derivative of the sine. Now, since it's plus in the middle, it really doesn't matter what order you do it. But for what we're going to do next, I think it's good to do it that way, just out of memory. So here's how we're going to write it today. So what did we get? We got 2x sine x plus x squared cosine x. That was our derivative. So the derivative of the first, leave the second one alone, plus the first one left alone times the derivative of the second. You take turns. Okay? Now, let's write that out. So the product rule says that if I'm doing the derivative of f of x times g of x, right? That's what this rule would look like in general terms. we do the derivative of the first, which would be f prime, times the g of x left alone, plus then the f left alone times g prime, right? That would be the product rule written out. Now again, which one you do the derivative of first doesn't really matter, but I would like for us to get in the habit of just doing the derivative of the first piece first with the second left alone and just do that. Okay, it's going to be helpful in some in the next rule we learn and then we memorize. Now here's how we usually will write this. This is the first you're seeing me use the letters U and V. For whatever reason, in the derivative rules, it just kind of become traditional, kind of like M for slope and B for y-intercept. It's kind of become traditional to use U and V instead of f of x and g of x. Now, one reason, now this is still U of x, and it's still V of x. So we could have just done f and g here, right? And written the same thing, because the whole parentheses x just is not really necessary to the rule. It just adds a bunch of other stuff in there that just makes it messier. So that's why a lot of times when we talk about f, we just talk about f, and f prime and f double prime. We don't put the x in there, but it could be there, right? It's kind of like back to the unit circle. In trig class, you just wrote x equals 3, or x equals cosine t. You didn't write x of t, but you know, it's there. It's just telling us t is the input variable. That's all that's saying. All right, so we typically do it this way. Notice, here's where Leibniz notation is important. Notice we're doing the derivative with respect to x. So u is just some batch of x's, and v is some other batch of x's. In our example, u would be the x squared, and v would be the sine x. Okay? So u and v just stand for some function that has x's in it. Okay, so it would be the derivative of the first, u prime, times v, plus u left alone, like that. So that's something that you will say in your head a lot, and you will just memorize. When I talk about the product rule a couple days from now, you'll go u prime v plus uv prime. That's how you'll think of it. U prime v plus uv prime. Okay, u prime v plus uv prime. U's first, then v. Okay, and so when you get to a problem, again, just think about taking turns, but when you get to a problem, you would probably write up here, you might even write, you say, well, this is going to be my u, and this is going to be my v. And so it's u prime, so there's u prime v plus u v prime, like that. Okay? So, pretty straightforward. Let's do a quick example. So let me just give you one that combines a few of the rules we've already been talking about. So let's say I gave you x plus 4 to the 5th times sine of 3x. Write down for me real quick here what you think the derivative of that would be. There's your u, there's your v. All right, so product rule, again, you can think of the u's and the v's or just think of taking turns. It's going to be the derivative of the first thing. So how do we do the derivative of this? Bring down the 5. What happens with the inside? Always stays the same. I often see people, I really want you to do well. I would love for 100% of you to pass this on the first try. I really would. Okay? And it just kills me when somebody has missed 2 already. They need to get the rest of right to get their 8. and then they get a problem like this and they forget to put the 4 right there. It's easy to do because you got all this other stuff going on. You write the 5, you write the x plus 4, and then you just forget about that guy right there. Matter of fact, when I'm doing one like this, a lot of times I'll do this. I'll just do that just to make sure. I'll just write it right away, and then I'll go fill my parentheses in. Do we kick out anything? When something's multiplied by the x on the inside, we kick that out, meaning multiply by it, but there's nothing there. Okay, now v would just be left alone. Right? Plus u would be just left alone times v prime. There's going to be a 3 kicked out, and it's cosine, and then the 3x left alone on the inside. Now, one of the things we'll talk a lot about over the next couple days will be how much do you have to simplify it? Is that good enough? Oftentimes, well, I don't know, half the time, maybe a little more, you do your first step of your derivative rule and you're done. But then there's going to be times where you need to simplify it a little bit. For example, let's say there had been a 6 out in front of this. Well, that 6 can multiply with that 3 and make 18. Okay? So that should be done. So there's often some simplifying. I like to call it obvious simplifying, but that's probably a bad word because what's obvious to me might not be obvious to you. So I'm going to try to teach you and let you know what's obvious. So other people might look at this and say, hey, you could take out an x plus 4 to the 4th, right? Did everybody see that? Yeah. You got this plus this, right? Here's my rule on factoring. The only time I would worry about factoring something is if you can then cancel to reduce. Otherwise, I wouldn't factor. In other words, if you get an answer that's 3x plus 6, I would just write it as 3x plus 6, not 3 parentheses x plus 2. I think that's just rearranging. Rearranging, I don't care about. But putting stuff together, I do. Like a 6 times a 3 makes 18. I think that needs to be simplified. And I think if you can cancel some things, you should do it. Now, like this 3 here, should that come around in front here? To me, that's just rearranging. So I'm not that worried about the 3 getting put in front of those 2 things there, right? To me, that's probably okay. I think you should, maybe as a habit. I think it's just neater and looks better. I think, so that's okay. But on the gateway test, if you had that, that would be okay. That would be okay. Don't need to just rearrange them. So we have to combine some of these rules we've already learned, like kicking out, you know, and that kind of stuff, along with these new rules. Okay? Anything on that? Anything else? All right. Now, Clay, let's do this one. Now we're going to do what happens if you divide. Makes sense that if we add or subtract, we just do their individual derivatives. If we multiply, we follow this rule. What happens if we divide? So let's do x squared over sine x. I just picked some nice ones here that work out pretty simple. What kind of an answer will we get here? So we go to our calculator and we let it do it. Now, the calculator did a weird thing there. It factored out an x, and let me fix that and write that in a better way. So let me distribute that x back through there. So that would make an x squared here negative, and it make this a positive 2x. Everybody with me? So if I distribute that back, whoops, if I distribute that back through there, this would be a negative x squared, and then this would be a plus with a 2x. Now I'm going to rearrange that. So I'm going to write this as 2x sine x minus x squared cosine x. That's what the top would look like if we were doing it. Okay? All over sine squared. Now what does it look like it did? Look at the top first. Didn't it do the same thing except a subtract instead? So it looks like it took turns. It did the derivative of the top, left the bottom alone, did a minus, and here's why the order matters here. So this is why I wanted you to do this with your product rule, because it's going to be the same order as this one. This is called the quotient rule, for obvious reasons. So the top derivative, leave the bottom alone, then a minus, leave the top alone, then derivative of the bottom, and then what goes down here? Whatever the bottom is, squared. That is the quotient rule. Now, any quotient can be turned into a multiplication, so you might say, why don't you just use the product rule? Well, we could bring the bottom up as a -1 power, but then that brings in a rule we haven't learned yet, so it doesn't really make sense to do that. Quite honestly, I think most of the time that's messier. I think the quotient rule is usually better but you could decide that it's not and do it that way, and it would work. Okay, so what did it give us? It gave us 2x with the bottom left alone, minus the x squared left alone, derivative assigned, the derivative of the bottom is that, all over the bottom squared, which we could write our cheating shortcut way like that. Okay, now here's where factoring might become an issue. Remember how the calculator took out an x, right? I would not take out an x. Why not? There's nothing on the bottom for it to cancel with. There's nothing on the bottom for it to cancel with. Now, if I had a sign in both of these and took out a sign and then could cancel it with one of the signs down here, then I would want you to do that. So, right? So factoring is only going to be an issue in a fraction type one, like a quotient rule, and only if you can factor something out of the top that would then cancel with something in the bottom. But otherwise, I would not factor an x out of the top there because it doesn't get me anywhere as far as canceling goes. Okay? And there's nothing else that I can combine, and so I would just stop, and there's my derivative. Okay? All right, let's write the rule. So, the quotient rule. Now, I'm writing it out both with F and G's, and I'm going to write it out with U's and V's, which is how we'll usually remember it, but there is a homework assignment or two, homework problem or two, where you want to write it with F and G, because they don't give you equations, they give you table of values, and I'll show you what that means in a minute here. So the derivative of f of x divided by g of x is f prime of x with the g left alone minus f of x times g prime of x, and then on the bottom is g of x squared. And that would be the same as u prime v minus uv prime all over v squared. That's the way we'll usually say it to ourselves as we're memorizing it and thinking about it. It's the same as the product rule on top, except it's got a minus in it, and then it's over the bottom square. So now if we have a sum of functions and a difference of functions, we know we can just do their individual derivatives and add or subtract them together. If they're multiplied together, we do the product rule. If they're divided, we do the quotient rule. And then, of course, it gets really fun when you have a product on top divided by another function on the bottom. So now you get to do a combination, right? So if you've got a quotient, if you've got a product on top, well, right here, when it comes time to do the derivative of the top, this part, you would do a product rule. Product rule within a quotient rule, and we get something. And so those will be the things we'll be working on between now and next Tuesday, because there's not a lot of rules. We have another rule we'll learn tomorrow, and then somebody mentioned the arc sine and arc cosine, which are a couple more, and then that's really it. A lot of our time is going to be spent practicing and looking at these things. Okay, so there's the quotient rule, so we got a little bit of time left here. I want to just talk about one thing that's going to be on your homework. So there's going to be some problems. One where you're going to have to fill out a table of values, and then I think there's another problem in there somewhere where this comes in. Most of your homework is simply practice doing derivatives, following these two rules, some products and some quotients. There might be some where they say do it two different ways. For example, I can't do this up there. Let me do it here. They might give you a function like this. Let me just do a real easy one. Like that, right? Now, one way to do this would be to just go, oh, well, that's x to the fifth, so the derivative is 5x to the fourth, right? Or we could do it with the product rule. the product rule, this would be your u, this would be your v. So the u would be derivative of the first, which is 2x times the x cubed left alone, plus x squared times the derivative of that,
Yes.
3x squared, which is 2x to the fourth plus 3x to the fourth, which is 5x to the fourth. So they say do it both ways. Do it by multiplying together first, doing the derivative, and then do the product rule. So just, you get a few of those where you're just kind of showing that, yeah, hey, the product rule is working, right? We would never do a product rule in this one, I don't think. We would just simplify it first and then do it. All right, so I want to show you that. Then you've got another set of exercises that does something like this. They'll say, okay, let h of x be f times g. Right? Let h of x be f times g, and they don't tell you what f and g are. So then they say find h prime of 2. Right? Well, before you can find, and I've said this to you before you can find h prime of 2, you first have to find h prime of x. So you have something to plug the 2 into. So what you need to do is do h prime of x. Oh, well, that's just the product rule. So that would be f prime of x times g of x plus f of x times g prime of x, right? And then h prime of 2 would be a 2 plugged in everywhere you see the x. So it would be f prime of 2 times g of 2 plus f of 2 times g prime of 2. Now maybe on one of the problems they give you a table, and it's got f of 2 and g of 2 and f prime of 2. They're all in there. You just have to grab them out of the table and plug them into that. And then, or you might be given maybe an f graph and a g graph. So you can find g of 2 by just looking at the g graph, find f of 2 by looking at the f graph, find f prime of 2 by doing what? On the f graph. F prime of 2 would be the slope on the f graph. And g prime of 2 would be the slope on the g graph, right? And you can estimate them or something like that. You see what I'm saying? So there'd be a case where you'd use the rule, but not have any functions to mess with. That's not going to be on the gateway test, okay, that we do, but it could be in some of the homework problems. So you use the rule, you plug a 2 in for x, and then you fill in those values. Or, since we don't have time to get started, let me just say one last thing. They might give you this problem, and I think they do on one of them in there. They say, is h increasing? So we bring the chart into it. Is h increasing at 2? Well, h is increasing at 2 if what? H prime at 2 is positive. So what would you do? You would work through this just like this to find out if h prime at 2 was positive. If it is, then yes, h is increasing. See, so it's a new way to look at an old thing using this new rule here. Okay? So the first line on there, now I had you do the odds there, so you can look them in the back, but again, you got your calculator. Remember, when you look them up in the back, it may not look exactly how you wrote them. So type it in your calculator and compare, do that kind of thing. So product rule and quotient rule. Might have some time to work on it during math testing. I don't know. I think you should really try really hard on your math test tomorrow. And, you know, you may need the whole 2 hours, but
I was trying to, I want to convince my grandkid that you want me to take all 3 the first day.
yeah. Probably not going to happen.
I'll make it ready.
It's your last math, well, seniors. It's your last math test ever, right? Because I don't think you guys have to in the spring. Now, who knows? I tell you that.
It's our last.
They may change their mind. Yeah, all of a sudden say, well, we decided.
We've had 5 last minute.
I did last time.
That's true. Last year, well, last year, because I've got seniors at Bear Creek too. I I told them that, yeah, they're soft, or in December they were done with map tests, and then they were, we're gonna make seed, we just had to make something to do it.
I'll talk to Mr. Ortega about it.
Okay.
I think he'll be okay.
Now you gotta remember to stop the recording.
We did.